So now we need to talk about the engineering forces. So how many fundamental forces did we say there are? 4, non-negotiable. It's only 4. How many did we say there are in engineering forces? Do we have a specific set number? No, in general. In general, we don't, okay? But in grade 11, we only talk about what? 5. In grade 12, we will add 2 or 3 more. And in first year physics or engineering physics, probably they will add 2 more. And I yet have to see more than 10 in general, okay? So we will say that there are many of these forces, since it really depends on how complex or what kind of a physical situation is being studied, okay? However, the ones we will be studying are the following, okay? And I'm going to say them not in order of importance. All of them are critical, just in the order, I guess, of the ones we will be subject to day after day. So the first one is, what's the first one? Gravity, not gravitational. They are related, but they are not the same. They are related, but they're not the same. Okay, next one. I know the name is weird. Normal force. I will tell you exactly why it's called normal. It's actually a name that did not come from physics. It actually came from math. I'll explain to you why. Next one is tension. Tension force. And then we have the friction force. And finally, absolutely, the applied force. Okay. Yeah. Okay. So let's talk about each one now. Okay. Can someone tell me again what was the definition of the gravitational force? By the way, it's in your notes. What was the definition of the gravitational force? Say wait a minute. Does the gravitational force ever push? It's always what? It's always attract, which means does it push them out or pull them in? It's always an inward pulling force. Now, okay, between what? Hmm. Okay, when we no, but hold on. I'm talking about gravitation. What did we define gravitation to be? It's the attractive force between any what? Any two objects in the universe that has what to it? Mass. That's it. Did we care about how big, sorry, not how big, how light or how heavy the objects were? No. Did we even care how close or far the objects were? No. We just know one thing. The further the two objects grow further, what happens to the force between them? Of course, it gets weaker, right? Okay. Gravity is very related to that, but gravity is the what? It's actually a specific situation of the gravitation. It's the force between a huge object, huge in mass, which usually happens to also be huge in what? Huge in volume or size as well. Okay. It's the force between a huge object, usually a planet scale, okay, and a small object. Very important. Where is a small object? On the surface or very close by. That's why gravity is different than gravitation. Gravitation could be between what? Two planets. Gravitation could be between what? A planet and the International Space Station. It could be between what? Two electrons separated by the diameter of the Earth. Whatever. Gravity, no. Gravity needs three things. Or what object first? A massive object and a what? And a tiny object. And where does the tiny object have to be? On the surface or super close by. By the way, you might ask a question. Well, how close by is close by? Like, how do I have to, like, what would constitute that I'm very far away that I cannot call myself close by? As long as the 9.8 meters per second squared applies, you are what? You are very close by. Because remember, the further you go from the planet, the further away you go. What happens to the acceleration of an object you just dropped? Does it accelerate faster or slower if you go really far? Exactly. So that means what? The further you go, you get more into what? Gravitation than what? Gravity. The closer you get more into what? Gravity than gravitation. Do you see the difference here? The distance mainly is the biggest difference. If you're really far, you cannot call it gravity. You have to call it what? Gravitation. If you're really close and the object is huge, you have to call it what? Gravity. Okay? All right. Can someone remind me again what was the symbol for all forces? All forces. What's the symbol for force? F. Small or big? So capital. And technically, is it a scalar or a vector? All forces are what? Remember, because it either could push or pull. Okay, I know that gravity only pulls, but in general, any force could either push or pull. So technically, it's a vector. So now we need what? We need some subscripts. Yes. So again, it's what? It's lower case g. That should also what? Emphasize in your head, that's what? Oh, it's like the g from what? From 9.8 meters per second squared. I have to be very close to the surface of the Earth. Oh, by the way, everyone, question for you. Does it have to be just, so my question is gravity only applicable to Earth? No. It's applicable to any what? Planet or heavy size what? Sorry. Big size what? Big size celestial object. So does the moon have gravity? It does. But compared to the Earth, it's much what? We're going to actually calculate that theoretically and compare to the actual experimental value of what? Dropping something on the what? On the surface of the moon, our moon. Okay, so F lowercase g. All right, next one. What was the next one according to the list? Normal. Okay. Yes. Or microgravity, as they call it sometimes. Yeah. Not from the Earth. No, but not from the Earth. Actually, there's technically no gravity on you when you're in the International Space Station. There is, but it's a very small what? Insanely small amount. That's why you keep what? Floating in space. Okay. Normal force. Where did the word normal come from? Probably no one here knows it yet. How many people here are hoping to go to take calculus and vectors? If you take calculus and vectors, you will hear this word every single day at the end of the vectors unit. Normal is just a fancy word that mathematicians use for the word. Nope. Which is what? Give me another word for 90 angle. Nope. Perpendicular. Thank you. Every time you hear normal, you just think what? Perpendicular. So the question now is, why is it called normal force? Because it's the what? It's the force a surface or any kind of flat plane, like even your hand pushes when it's pushed on by an external force. So let me give you an example. Does the board look like a flat plane? Yes, this. So that means if I hit it, does it hit me back? Of course it does. Think about it. What is the most famous Newton's law? Which one? First, second, or third? How many people know Newton's third law? It's the most famous. Every action has a what? Has a reaction. Equal in magnitude, but opposite in what? In direction. So when I push on a what? If I push on it exactly this way, is my hand perpendicular to the board? Yes, it is. Which means the board is also going to push what? Backward, which means it's also what? The force coming out of the board on my hand has to be what? Has to be, or what? Perpendicular. Do you see what I mean? That's why it's, okay, what if you push in a tilted way? Is that my question? Yeah, that's the thing. When we discuss Newton's third law, we have to actually see, and we will see that the magnitude is always the what? The exact same. It's the effect that's a bit confusing to think about. So don't worry about that. But my point here is what? If you push on a surface, how does the surface push back? Straight back. But in which way? Exactly 90 degrees to the surface itself. Okay, here's my question now. What do you think the symbol for the normal force is? I mean, it has to be a capital F, but what's the symbol? What's the subscript? N. And for most part, I've always seen it as uppercase N. Uppercase N. That's it. Yes? Yes. The pain I feel, the pain. Okay, question for you. If I punch very lightly, do I feel a lot of pain or barely any pain? Because that means what? I gave in a little force. It also gave in what? A little force. But if I push, it is the exact same amount of force, but they're acting on different bodies. I am acting on the board. The board is acting back on me. Okay. So again, we will discuss Newton's third law almost for a full day. Wait, so like, okay. Drop like a ball on like ground. Yes. Why do you think it bounces back? Again, what if it doesn't push? It should just stay there. But pushing up means something pushed it up. Yes. Tension. When do you only see tension? Well, tension needs something to be what? Okay, so you need something to be what? Either stretched or compressed or twisted. Thank you. You can say these three things in one word. Okay, everyone. Basically, in engineering, they call it what? Deformation. When an object gets deformed, that means what? It changes its what? Shape, but without changing its what? Mass. Thank you. So it's still the same amount of mass, but the dimensions of the object have changed. maybe it got what? Longer or shorter, or it got what? Twisted. Whenever you actually, like a spring, you can what? Stretch a spring. You can also what? Compress a spring. And technically, you can also what? Twist a spring or twist a shopping bag, right? Whenever you do any of these things, what force are you going against? Tension. Whenever you do, you change the shape, but not the mass, change the dimensions, you are going against the what? Or you're doing the what? The tension force, okay? So the tension force is whenever something gets compressed, stretched, or twisted. Where, by the way, so here's a question now. In grade 11 physics and also grade 12, where mostly will you need to consider the what? The tension force. If your problem ever includes what? If it includes ropes, strings, cables, chains, anything that could be deformed. Anything that could be deformed definitely has what? Has a tension force inside of it. Inside of it. Do you also can you see tension force in your body? Yes, of course. You go to the gym every single day and you do biceps curls for every single day. What happens here? I had it right here. Stretch marks. Every guy who goes to the gym does 5 biceps curls every single day, right? Because they want to do the guns. Yeah, but then what happens? What happens? Yeah. What, by the way, what are stretch marks? It's like a rubber band that you what? That you what? Stretched, but you did not let go to what? To the natural state. Every single time you stretch more. So what happens to the bonds inside? Eventually, what happens to them? They stretch out, they get broken, they basically tear, and they never go back to what? Instead of becoming elastic, it becomes what? It becomes plastic. Elasticity means what? You go back fully. Plasticity means what? That's it. You are not malleable or you're not resilient anymore. Okay? Now, what's the symbol for what? What's the symbol for tension? I've seen it in every book in one of two ways. Either F with capital T or just what? Just, yeah, just capital T. Depending on how much space I have on my diagram, I might use FT, but I'm just going to tell you from now on. I'm always going to use what? I'm always going to use capital T, just the T. Yeah, everyone, go ahead. Circle this one, circle this one, circle this one, and say most common. Circle the T, just the T, capital T, and say most common. But here's the thing, though. Sometimes you're dealing with what? Multiple tensions. So you have to call it what? FT1, FT2, FT3. Like you have multiple ropes. Well, it's easier to call it what? T1, T2, T3. You got it. All right. What's the fourth one? Friction. Come on. What does friction do? What's the job of friction? All the time. Okay. So it's good what? Heat stuff up. What does it always do? Say again? It is the responsible force for what? Slowing something down and even bring it to a complete what? If it could. If it could. But at least it's going to what? It's going to slow it down. Okay? So does friction ever, everyone, does friction add energy to the system or steal energy from the system? Yeah, because if it adds, you should get faster or you should be able to do more or you should travel further. Well, guess what? Friction always what? Friction always steals energy from the system. By the way, there are two kinds of friction. Remember what force we said we're not going to deal with if we do gravity? What force are we going to assume it doesn't exist? Air drag. Technically, air drag is a part of what? Is a form of what? Sorry. Is a form of friction. That's called what? Medium friction. Whenever you are going through a medium, you call it medium friction. Whenever you're going across a surface, you call that surface friction. We never do medium friction. I told you, drag is very complicated to do, both mathematically and geometrically. We only do what? Surface friction. We only do surface friction. Okay? Friction usually is taught as a positive or a negative thing. Usually. Negative thing. But actually, it is what? I mean, when you're driving in the snow, you need what? You need friction. Otherwise, we'd have even more accidents. Is it making sense? So friction is actually could be your best friend or your best enemy, depending on what you want to do. Okay? All right. What's the last one? How could we define the applied force? What's the easiest way to apply the applied force to define? Easier way. You're right. It's how you apply a force on something. But what's an easier one? Yes. There's an easier way. It's any force that's not the first four. Right? If it's not friction, if it's not gravity, if it's not normal, and if it's not what? No. Tension, it has to be what? It has to be applied force. Unless you can say it's one of the first four, you can just say what? it's an applied force, which usually is going to be what? Some external agent, just what? Just what? Pulling on an object. Is it making sense? Or pushing? Anything else, we already have a name for it. Whatever else, we're going to call it applied. Okay? Oh, why do you think? Why do you think we always have to define multiple ones? Of course, that's tomorrow's job when we actually do what we call system diagrams. And how many people have heard of free body diagram? Free body diagram is the most important diagram you can sketch in a force problem. It's where you put all the what? All the forces on it together, and you do what? A vector analysis. You're right, but obviously, yes, there is no point of me giving you a force problem with only what? One force on it. I'm at least gonna give you, I mean, usually the maximum I could give you is what? Or all five. Okay. How many symbols are there for the applied force? Honestly, whatever you want to call it. You can call it what? FA for applied. You can call it FAPP for applied. You can call it FB or FC. Or for example, what if it's a force done by Ali? We can call it FALY, for example. So any name would do as long as you know exactly what it refers to. Kind of like the relative motion, right? You just have to choose the subscript as long as you know what the subscript refers to. Okay?